Hello guys, how are you? In this video we are going to talk about work energy, and we are going to see how to calculate the work done in the form of change in energy in different cases. Let's dive in. Now let's consider first a mass on a horizontal surface. There's a horizontal surface. If this is the horizontal surface, then you have a mass. Then now you apply a force on the mass, a force F. Now the force is F, which is just a constant amount of force on the surface is smooth, so this is a mass M. By applying a force, you displace the mass to this position, so this is a distance S. Now we know from the definition of work done is equal to force times distance. If there is a component, if the angle is not parallel to the force vector, if the force vector and the displacement vector are not parallel, so you do the work done is equal to the force times cosine of the angle between the displacement and the force times the distance. Now I'm going to explain how to drive expression for the work. Now you have a mass M. Now by applying a force F on the mass M, you change the speed of the mass from a certain u, consider u b0, the initial speed b0, to a certain final speed v, because the mass possesses some amount of energy more due to this force, meaning some mechanical energy will be transferred to the mass because of this force. That work done is equal to the force times the distance. But the force is how much? The force is the net force, because the surface is smooth. We consider the surface to be smooth, meaning friction is zero. So the applied force and the resultant force gonna be equal, meaning the force resultant and the applied force are equal, and it is also equal to the mass times acceleration, like this. Now the work done is gonna be how much? The mass times acceleration times the distance. This is the same as the acceleration is from Newton's second law. We have used this one, and from the definition of acceleration you can use acceleration is the final speed minus the initial speed divided by time. But the initial speed is how much? In this case you can consider the initial speed to be zero, but the work done is equal to the mass times the acceleration is the final minus the initial divided by time, multiplied by the distance in accelerating motion, the final plus the initial over 2 the average speed times the time. Then when you simplify this, it's gonna give you what? It's gonna give you the work done is equal to the mass into the v square minus the u square over 2. Or you can write this one, the work done is equal to the half of, this work done is equal to half of the mass into the final speed square minus the initial speed square. But when you distribute this, you're gonna get half of the mass times v square minus half of the mass times the initial speed square. You know from your lower grade physics or science, general science, half times the mass times u square is how much? This is the kinetic energy of the mass final, but this is the kinetic energy of, again, this half of mass times u square is the kinetic energy of the mass initial. So simply here the work done is equal to how much? The change in kinetic energy, which is 1 over 2 times the mass times v square minus 1 over 2 times the mass times u square. Now you can simplify this as the work done is equal to half of the mass into the v square minus the u square. In this case, work is done only to change the kinetic energy of a mass, which is given by half times the mass times v square minus u square. Now in the case where u is the kinetic energy, the expression for the final kinetic energy will be the same as the expression for the work done. So in the case where u is 0, so the work done is going to be half times the mass into v square minus 0 square will give you half times the mass into v square. So in the case when the initial speed is 0, the work done is the same as the kinetic energy final. So the expression for kinetic energy gonna be the same as the expression for the work done in the case where work is done from starting from rest to change the speed of a mass on a smooth horizontal surface. Now let us see this example. How much kinetic energy is possessed by a 10 kg mass moving with a speed of 10 meters per second? Now we are given the mass. Here you are given the mass is given. The mass is how much? It is 10 kg, and the speed is given. It is 6 meters per second. Now the question is how much kinetic energy. Now you are required to find the kinetic energy. So kinetic energy is equal to 1 over 2 times the mass times the speed squared. Now this time the mass is 10 kg times the speed is 6 meters per second square. Actually kg is here, so kg times meter square per second square. So this gonna give you half of 10 is 5 times 6 square is 36 times kg times meter square per second square. Now so you can simplify this as 10 over 2. You can write instead of 5 10 over 2 times 36 kilogram dot meter per second square is joule. So you can say this is equal to how much? 10 times half of 36 is 18. So the energy process is 180 joule. This time we are required to calculate the work done. How much work is done to change the speed of 10 kg mass from rest to 6 meters per second. Now you can calculate here the change in kinetic energy as the work done. So the work done is equal to the change in kinetic energy, but this is equal to kinetic energy final minus kinetic energy initial. This is the same as 1 over 2 times the mass times V final square minus 1 over 2 times the mass times the initial speed square, U square. So you can take half the mass as common. So the work done is equal to how much? The work done is equal to half of the mass times V square minus U square. So this is the same as 1 over 2 times the mass times 6 square minus 0 square. So this will be how much? 1 over 2 times 10 kg times 36, sorry. So this will give you how much? 180 joule, meaning due to the force to change the speed of the mass, so from 6 meters per second, from rest to 6 meters per second, so you are doing work on the mass. So in the case when you do work on a mass, on work done, work on a mass, what would happen? Energy of the mass increases. But when we do work by a mass, what happened? The energy of the mass will decrease. Now there is a mass, you apply a force on it, so through the help of this force, energy will be transferred to the mass. So the energy of the mass will increase. In the other case, if you have a mass, here is a mass, and if you have another mass here, right? So if you collide this mass, the speed of this mass will be decreased and the speed of this one will be increased. Now the energy of this one will be, the kinetic energy of this mass will be decreased, the kinetic energy of this one will be increased. Now work is done on the circular mass by the rectangular mass. So the energy of the rectangular mass is decreased and the energy of the circular mass will be increased. In this case, we are going to see how to calculate the work done to change the height of a mass. Now there is a mass initially here, so the mass is pulled by a force F. The force F is the same as mg. Then the mass moved from the initial level A to level B with a constant speed. The speed is not changing, so that the kinetic energies are not changing. So the work done by the definition is the force times distance, but the force is how much? The force is the weight, the mass times gravity, times the distance is the height. So the work done is equal to how much? The mass times g times the change in height. So this is the change in height between level A and B. Yeah. So you can write the change in height here, but you can have another height here, h1. You may move this mass from h1 to another mass another elevation h2 like this. So the work done here is equal to mg times the change in h, but the change in h is how much? h2 minus h1. So the work done here is how much? The mass times gravity times h2 minus h1. So the work done is equal to mass times gravity times height 2 minus mass times gravity times height 1. Now this is gravitational potential energy 2, but this is gravitational potential energy gravitational potential energy 1. Gravitational potential energy 1. Now you can see here the work done is equal to the change in gravitational potential energy. So if height 1 is 0 gravitational potential energy level, so if this is 0 gravitational potential energy level, then the work done is going to be how much? The mg into h2 minus 0. So this is going to be mg h2. So analogous to the previous one, the work done is going to be how much? The mg times h2. But the mg h2 is the expression for gravitational potential energy 2. So the formula for gravitational potential energy is how much? It is the mass times gravity times the level where the mass is, h, the height h. But the work done to change the gravitational potential energy of a mass, to change GPE, gravitational potential energy, is given by mg times change in h, the change in height. So this is how you calculate the work done. Now let us do this example. How much gravitational potential energy is possessed by a mass there's a mass is 10 kg, yeah, 10 kg at a height of 8 meters. So you are given the mass is 10 kg, and you are given the height is 8 meters, and you are given you can use gravity 9.8 or 10 meters per second square for the sake of simplicity. Now you are required gravitational potential energy is how much? Now the formula to calculate gravitational potential energy is gravitational potential energy is the mass times the gravity, acceleration due to gravity, times the height. So this is equal to how much? 10 kg times 10 meters per second square times 8 meters. Okay, so this will give you 800 kilogram dot meter square per second square, which is joule. So this is equal to how much? 800 joule of energy is possessed by that man. So how much work is done now to change, how much work is done to change the height of a 10 kg mass by 8 meters. So this time the mass is given 10 kg like the previous one. So the gravity, acceleration due to gravity is 10 meters per second square, and the change in height is given, it is 8 meters. Now work done to change the gravitational potential energy is required. Now how do you do this? The work done to change gravitational potential energy, to change GPE, is equal to how much? The mass times gravity times the change in elevation. Remember, gravitational potential energy is how much? Gravitational potential energy is simply mg height. This height is not change, but when you calculate work, it is a change. So this is equal to how much? 10 kilogram times 10 meters per second square gravity times the change in height is 8 meters. So this will give you 800 meter. I mean 800 kilogram meter square per second square. This is gonna give you the work done is equal to 800 joule. The other form of energy is elastic potential energy, also called strain energy. Strain energy is a kind of energy stored by elastic materials. Consider a spring which is free position here, it is free here. So where there is no force acting on the spring, it remains here. You can apply a compressive force, okay, a compressive force to get some change in x, or you can apply an extending force to get the same change in x. So a spring, either compressed or stretched, will possess a form of energy called strain energy or elastic potential energy. Now let's have a detail of this one. So you need to apply a force either to extend or to compress the spring. Now, from Hooke's law, the force you applied to the elastic material, which is the applied force, is equal to the stiffness of the spring times the change in length x. But the work done by this force is equal to how much? The average work done, the average of the initial and the final work done. So the average is given by the mean of the initial and the final divided by 2, because the work and the force and the force and the force and the displacement had a linear relationship. So the initial work done is 0, but the final work done is how much? It is force times distance, but your force is k times x and times your distance is again x. So the work done final is k times x squared. Sorry, kx squared. K times x squared. Now the average work done is equal to 0 plus k times x squared divided by 2. This is equal to kx squared over 2. So the work done to change elastic potential, EPE of elastic material is given by how much? From rest is given by the change in elastic potential energy. Now you can have a spring, yeah? You can have a spring, a free position of the spring, maybe some support is here. So maybe the spring is free here, and you can apply a certain force to change the spring to this position. But this may be what? X1 extended, but you can further extend this one to here by some force. Now this distance is gonna be the other x2. Okay, now the question is how much work is done to extend from this level B to level C, the final level. So in order to extend this spring from level B to level C, there is some work done. The work done is equal to the change in elastic potential energy of the spring, meaning the work done is half of k times x final square. It is elastic potential energy final minus half of k times x initial square, the initial elastic potential energy of the mass. So the work done is equal to how much? Half times k times x final square minus x initial square. Now this is how you calculate the work done only to extend the length of elastic material. Let's have now a certain elastic material spring. So this is the free position of the spring. So where there is no force acting on the spring remains here. So you apply a certain F1 to extend the spring by 10 centimeters, provided that the force applied is less than its elastic limit. Another force, you applied larger force F2 to bring the the extension to 40 centimeters. Consider this is F2 is also a force less than the elastic limit of the spring. Now, the question is, you are supposed to calculate, all right, the elastic potential energy of A, elastic potential energy of B, elastic potential energy of C. All right. Now, the formula for elastic potential energy is, you can see A is rest level. There is no extension. So XA is how much? It is 0. So the initial elastic potential energy of A is half times the stiffness times K X square. XA square. So this is how much? X half of K times XA square. But how much is K? K is 2000 Newton per meter. The stiffness is 2000 Newton per meter. So this is equal to half of times 2000, all right, times 0, gonna give you 0 joule energy. There is no any energy stored by elastic material when the elastic material is its rest position or equilibrium position. Now the second question is, you are required to calculate elastic potential energy of B. So elastic potential energy of B is half of K times XB square. All right. So you can see the position B is this one, X1. This is XB. X1 is like XB, and X2 is like XC. Okay. Consider this as XC. So the force is applied, and the stiffness is 2000. Now how much is XB square? Now this is equal to 1 over 2 times 2000 is the stiffness times 10 centimeter. Okay, 10 centimeter is 10 over 100 meter. So you are supposed to that square. So this is equal to half of 2000 is 1000. So 1000 times this is 1 over 10, 1 over 100. The square of this is 1 over 100. 1 over 10, you can cancel 1 over 0. So when you square it, 1 square over 10 square, that's gonna give you 1 over 100. So this is equal to how much? 10 joule of energy is stored when the elastic material is under position B. Now in case of position C, so at C, you are looking for elastic potential energy when it is at C. So this is equal to how much? This is equal to half times the stiffness times the extension of C square. So this is equal to 1 over 2 times 2000 times 40 centimeter. 40 over 100. You just square this. So 4 over 10, 16 over 100. So this is gonna give you 1 over 2 of 1000 is how much? It is, 1 over 2 of 2000 is how much? It is 1000 multiplied by, this is 4 over, you can say it's 0.4 or 4 over 10. So when you scale 4 over 10, that is 16 over 100. Yeah. So 16 over 100 is 4 over 10 square. That is joule. Now you can omit the 2 zeros. So this is equal to how much? 160 joule of work. Energy is stored. Now we are required to calculate the work done. It says how much work is done. To extend the spring from A to B, from A to C, from B to C. So the work done from A to what? To B is equal to how much? The energy of B, the elastic potential energy of B minus the elastic potential of A. So this is equal to how much? We have already done the elastic potential energy of B. This B is EPE at level B is how much? It is 10 joule. All right, we have already done. And the elastic potential energy of C is how much? EPE, elastic potential energy of C is how much? 160 joule. Then, so the work done from A to B is how much? From A to B is 10 joule is the energy of B minus 0 joule is the energy of A. So this is equal to 10 joule. So 10 joule work is done in extending the spring from this level to that level by 10 centimeter. Now, how much work is done to extend the spring from A to C? This is the same as the energy of C minus the energy of A. The energy of C is 160 joule minus the energy of A is 0. So this will give you 160 joule. Now the last question is, how much work is done to move the mass, the spring, from B to C. So the work done from B to C is the energy of C minus the energy of B. The energy of B. So this is equal to 160 joule minus the energy of B is 10 joule. So this is equal to how much? 150 joule. So this is the amount of work done. This is the last example we have. Let's try to summarize what we have already done so far. So we have two forms of energy. So we have kinetic energy, which is 1/2 times the magnitude of the mass times the speed squared. We have gravitational potential energy, which is mass times gravity times height. And we have the elastic potential energy, which is half times kx squared. Now, work done is the amount of energy transfer or transform. So the work done has different formulas. In the case you have force and displacement, you put the force cos theta times the distance. But work done generally is equal to the change in energy. If this for smooth surface, this is for smooth, there is no friction, yeah. For smooth surface, yeah. For smooth surface, we have the work done is equal to the change in energy. Now, what kind of energy is changing in a given process? So if the kind of energy is changing, kinetic, for work done to change kinetic energy of a mass, it is given by kinetic energy of the mass final minus kinetic energy of the mass initial, half times the mass times v square minus u square. And the work done only to change gravitational potential energy is given by, gravitational potential energy is mgh. So its work done is equal to how much? Mass times gravity times the change in height. This is how you calculate the work done only to change the mechanical energy, the gravitational potential energy of a mass. There's another thing to note, the work done to change elastic potential energy, EPE is given by elastic potential energy final minus elastic potential energy initial. So this is given by half k times x final square minus half k times x initial square. So this is the same as the work done to change elastic potential energy is given by half k into x final square minus x initial square. Now, the work done to change mechanical energy, the work done to change mechanical energy of a mass is equal to the change in elastic potential energy plus the change in kinetic energy, if any, plus the change in gravitational potential energy, if any. So this is equal to half times k times x final square minus x initial square, if any, plus half times the mass into v square minus u square, if any, plus mg times height 2, the elevation 2, minus the final elevation. You can say the final elevation h final minus h initial, or you can say this is equal to simply half times k into x final square minus x initial square, if any, plus half times m into v square minus u square, if any, plus mg times the change in h. So this is the work done to change the mechanical energy of a mass. Thank you for watching this video. So please don't forget to share and subscribe and comment on the video so that I can correct, I can just improve the videos which is very good for you guys. I will have another video on the other topics. Thank you for watching.